Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home, on your commute, or winding down for the evening, I'm really glad you're here. Now, I want you to imagine something for a moment. Picture yourself as a detective, but instead of solving crimes, you're solving cosmic mysteries. And instead of fingerprints and DNA evidence, your only clues are numbers, tiny, almost imperceptible numbers that most people would dismiss as measurement errors. But you see something else entirely. You see the signature of an entire world hiding in the darkness, 4 billion kilometers away. This is exactly what happened in 1843, when a young French mathematician named Urbain Le Verrier found himself staring at some very troublesome numbers. These weren't dramatic, obvious problems. We're talking about deviations so small they measured just minutes of arc. To put that in perspective, that's about the width of a human hair held at arm's length. Imagine trying to spot that from across a football field. That's how tiny these discrepancies were. But here's the thing about Urbain Le Verrier. He was the kind of person who couldn't let sleeping dogs lie. When the numbers didn't add up, he didn't shrug and move on. He dug deeper. And what he discovered would fundamentally change how humanity explores space. So, what exactly was bothering Le Verrier? It was Uranus. Yes, that planet that everyone snickers about because of its name. But back in Le Verrier's time, Uranus represented something much more profound than a source of juvenile humor. It was the first planet discovered in modern times, found by William Herschel in 1781. For the first time in human history, we had expanded our known solar system beyond the classical 5 planets visible to the naked eye. Now, when astronomers discover a new planet, the first thing they want to do is figure out its orbit. It's like learning the rhythm of a cosmic dance. And for a while, everything seemed fine with Uranus. It followed Newton's laws of gravity beautifully, orbiting the sun in a predictable mathematical ballet. But then something weird started happening. As the years passed and astronomers tracked Uranus more carefully, they noticed it wasn't quite where it was supposed to be. It was wandering, just a little bit, mind you. But in astronomy, a little bit can mean everything. Picture this. You're watching a train that's supposed to arrive at exactly 3:15 p.m. every day. For years, it's been punctual to the second. Then one day, it's 3 seconds late. The next day, 5 seconds. Then 10. You might think, well, trains are late sometimes, but what if I told you this train runs on the most precise clockwork in the universe? What if those few seconds of delay meant something much bigger was going on? That's exactly what Le Verrier was facing with Uranus. The planet was arriving late to its predicted positions in the sky. Not dramatically late. We're talking about those hair-width deviations I mentioned earlier. But for someone who understood celestial mechanics as deeply as Le Verrier did, these tiny errors were like neon signs flashing, "Mystery here." Now, here's where it gets really interesting. Le Verrier had 2 choices. He could assume that Newton's laws of gravity were wrong, a pretty radical idea considering they'd successfully explained every other planetary motion for over a century. Or he could assume that Newton's laws were correct, but that something was tugging on Uranus that they couldn't see. Le Verrier chose option 2, and this decision would lead him down one of the most extraordinary rabbit holes in the history of science. Working by candlelight in his Paris office, Le Verrier began what can only be described as mathematical detective work of the highest order. He had to work backward from those tiny wobbles in Uranus's orbit to figure out exactly what could be causing them. Think about how challenging this is for a second. He's essentially trying to deduce the existence, location, mass, and orbit of a completely unknown planet based solely on its gravitational influence on another world. It's like trying to figure out the exact size, weight, and location of someone based only on the footprints they left in sand. Except the footprints are on a beach 4 billion kilometers away, and you're working entirely with mathematical equations. Le Verrier spent 3 years on this problem. 3 years of calculation after calculation, checking and rechecking his work, refining his estimates. He had to account for the gravitational influence of every known planet, the Sun, even the major asteroids. He had to strip away all the known influences on Uranus until only the unknown remained, and slowly a picture began to emerge. Whatever was pulling on Uranus had to be massive, much more massive than Earth. It had to be far away, much farther from the Sun than Uranus itself, and most importantly, it had to be in a very specific location in the sky. But here's where the story gets even more incredible. While Leverrier was burning the midnight oil in Paris, a young English mathematician named John Couch Adams was doing exactly the same thing in Cambridge. Neither man knew about the other's work. They were like two detectives working the same case in complete isolation, following the same clues to the same conclusion. Adams had actually started his work a year before Leverrier, but he was more cautious about publishing his results. He'd been troubled by the same orbital irregularities in Uranus, and he'd come to the same conclusion. There had to be another planet out there. Think about this for a moment. Two brilliant minds, working independently, using nothing but mathematics and the tiny gravitational whispers of a distant world, both arrived at the same stunning conclusion. There was an eighth planet in our solar system, and they could tell you exactly where to find it. Now, you might be thinking, okay, great theory, but how do you prove it? After all, having mathematical evidence of a planet is one thing. Actually finding it in the vast darkness of space is quite another. This is where things get both exciting and frustrating, depending on which side of the English Channel you were on. Leverrier had finished his calculations by 1846 and was ready to go planet hunting. But here's the catch. He needed someone with a really good telescope to actually look where his math was pointing. Leverrier approached French astronomers first, but they were skeptical. I mean, can you blame them? Some mathematician walks up to you and says, "Hey, point your telescope at this specific spot in the sky because I calculated that there's a planet there." It sounds pretty far-fetched, even today. But Leverrier was persistent. He wrote to Johann Galle at the Berlin Observatory, asking him to search a specific region of the constellation Aquarius. Leverrier's math had narrowed down the location to within 1 degree. That's about twice the width of the full moon in the sky. Here's where the story becomes the stuff of legends. Galle received Leverrier's letter on September 23rd, 1846. That very night, the very same night, he decided to take a look. Picture the scene. Galle and his assistant, Heinrich de Rest, are in the observatory with Leverrier's coordinates in hand. They point the telescope toward Aquarius and begin their search. They're looking for something that doesn't quite belong, a star that might be moving against the background of fixed stars. And then it happened. Within just 1 hour of searching, they found it. A bluish object that wasn't on their star charts, sitting almost exactly where Leverrier's mathematics had predicted it would be. Let me repeat that because it's absolutely mind-blowing. Using nothing but pencil, paper, and mathematical genius, Leverrier had predicted the location of a new world 4 billion kilometers away with such precision that astronomers found it in a single night of searching. The discovery sent shockwaves through the scientific community. Here was proof that mathematics could be used not just to explain the universe, but to discover new parts of it. It was like having a cosmic GPS that could guide you to worlds no human eye had ever seen. But the story doesn't end there, because now we get to the messy part, the part about who deserves credit for one of the greatest discoveries in astronomy. Remember John Couch Adams? He'd actually calculated the position of the new planet even earlier than Leverrier, but he'd been more cautious about publishing his work. When word of the discovery reached England, British astronomers were furious. They felt their countryman had been robbed of the credit he deserved. What followed was a scientific controversy that lasted for decades. The French championed Leverrier as the true discoverer, The British argued for atoms. Newspapers picked sides. National pride got involved. It was like a 19th century version of a Twitter flame war, except instead of arguing about celebrities, they were arguing about planetary mathematics. Today, we generally give both men credit for the discovery. They're both recognized as co-discoverers of Neptune. They're BAB. Yes, that's what they eventually named this new world. The name Neptune, after the Roman god of the sea, seemed fitting for this distant blue world that had hidden for so long in the cosmic ocean. But you know what I find most remarkable about this whole story? It's not just that they found a new planet, it's what the discovery represented. For the first time in human history, we had used pure mathematics to reach out across billions of kilometers of space and touch a world we'd never seen. Think about the audacity of that. Leverrier looked at some tiny wobbles in another planet's orbit and said, "There's a whole world out there causing this." He then spent 3 years calculating exactly where that world should be. And he was right. This discovery fundamentally changed how we explore space. Before Neptune, astronomy was largely about observing what we could see. After Neptune, it became about using mathematics to predict what we should be able to find. It opened up the possibility that our cosmic neighborhood might be much larger and stranger than we'd ever imagined. And here's the kicker. Leverrier's mathematical techniques would go on to be used for discovering asteroids, predicting the paths of comets, and eventually finding planets around other stars. The same basic principle, IOL, using gravitational influences to detect unseen objects, is still used today by astronomers hunting for exoplanets and even dark matter. But perhaps most importantly, the discovery of Neptune taught us something profound about the power of human curiosity and intellect. When faced with a tiny discrepancy that most people would have ignored, Leverrier and Adams saw an opportunity to expand human knowledge. They refused to accept that those little wobbles in Uranus's orbit were just measurement errors or random noise. Instead, they asked the most powerful question in science: what if there's more to this story? That question led them to a new world, and as we'll see in our journey together, that new world turned out to be far more extraordinary than anyone could have imagined. Neptune wasn't just another planet to check off our cosmic inventory. It was a world of extremes that would challenge everything we thought we knew about physics, weather, and what's possible in our solar system. So, as we prepare to dive deeper into the mysteries of Neptune, remember this. Every great discovery starts with someone noticing that the numbers don't quite add up. Sometimes the universe whispers its secrets in the language of mathematics, and it takes someone brilliant enough, and stubborn enough, to listen. Next time, we're going to take an impossible journey together. We're going to descend through Neptune's atmosphere, through winds that would make Earth's most powerful hurricanes look like gentle breezes, down into depths where the very nature of matter transforms into something alien and wonderful. Are you ready to fall into the blue abyss? Imagine you could take an impossible journey, not in a spacecraft, those would be torn apart in seconds, but as a conscious observer, somehow protected from the violence you're about to witness. You're going to fall through Neptune itself, from the edge of space down to the very heart of this alien world. And trust me, what you'll experience along the way will rewrite everything you thought you knew about weather, pressure, and the physics of matter itself. Your journey begins 500 kilometers above Neptune's cloud tops, where you're floating in what barely qualifies as space. The first thing that hits you, literally, is the cold. We're talking about minus 218 degrees Celsius. That's cold enough to freeze oxygen solid. Cold enough that if you brought a thermometer from Earth, the mercury would have turned into a rock long before you got here. But you know what's really wild? You can see aurora dancing in the sky around you. These aren't like Earth's aurora, though. These are methane aurora, glowing in frequencies your eyes would never normally detect, painting the darkness in ethereal blues and greens. The magnetic field here is so twisted and complex that these lights appear in places that would be impossible on Earth. Now, here's where things get immediately crazy. You start to fall, and the first sensation that hits you isn't the acceleration downward, it's the wind trying to carry you sideways. We're talking about winds moving at 1,200 miles per hour. That's nearly twice the speed of sound. These aren't just really fast winds, these are atmospheric currents moving at velocities that would shred steel. Think about that for a second. The fastest winds ever recorded on Earth were about 200 miles per hour during severe hurricanes. Neptune's regular, everyday winds are 6 times faster than that. It's like the entire atmosphere is locked in a permanent state of supersonic fury. As you fall deeper, the gravity starts to make itself known. Neptune pulls about 3% stronger than Earth, which doesn't sound like much until you realize you're also accelerating through increasingly dense atmosphere. Every breath, if you could breathe, would contain more and more material. Not just hydrogen and helium like you might expect, but traces of methane that give Neptune its stunning blue color. Here's something that's going to sound impossible. Those methane molecules are what make this world so beautiful and so terrifying at the same time. Methane absorbs red light and reflects blue, which is why Neptune appears as this gorgeous deep azure marble when photographed from space. But methane is also incredibly reactive. Under the pressure and radiation conditions you're falling through, it's constantly being torn apart and reformed into more complex molecules. At 50 kilometers down, you hit the first major milestone, every one. The pressure has doubled from what you experienced at the edge of space. But this is just the beginning. In Neptune's atmosphere, pressure doesn't increase gradually like it does on Earth. It doubles every few kilometers. So at 100 kilometers down, you're experiencing 4 times the pressure. At 150 kilometers, it's 8 times. The mathematics is relentless and terrifying. The temperature, meanwhile, starts doing something really weird. Instead of getting warmer as you fall deeper, which is what happens on Earth, Neptune's temperature actually stays remarkably constant through the upper atmosphere. You're still experiencing that bone-crushing cold of minus 200 degrees, even as the pressure around you builds to levels that would compress your body to a fraction of its normal size. But here's where your journey starts to get truly alien. At around 200 kilometers down, you encounter your first methane clouds. These aren't like any clouds you've ever seen on Earth. They form and dissolve around you in patterns that seem almost alive, swirling in spirals and eddies driven by those supersonic winds. The methane ice crystals catch and scatter the faint sunlight in ways that create an otherworldly light show. Remember, you're still falling at tremendous speed, but those 1,200 mile per hour winds are carrying you sideways even faster. If you could somehow mark your position and watch from space, you'd see yourself tracing a diagonal path through the atmosphere, moving horizontally much faster than you're moving vertically. It's like falling through a sideways tornado that never ends. At 300 kilometers down, something remarkable happens. The pressure has become so intense that the boundary between gas and liquid starts to blur. This is where things get really mind-bending. You're not hitting an ocean surface like you would on Earth. Instead, the atmosphere is gradually becoming an ocean without you ever noticing the transition. Picture this. The hydrogen and helium around you are being squeezed so tightly that they start behaving like a liquid, but they're still hot enough to remain gaseous. You're falling through what scientists call a supercritical fluid, ISPE, matter that's neither quite gas nor quite liquid, but something in between. It's like being inside a substance that can't make up its mind about what it wants to be. And this is where your journey takes a turn toward the truly spectacular. As the pressure continues to build and you fall deeper into this supercritical ocean, the methane that's been getting torn apart by radiation and pressure starts to do something extraordinary. The carbon atoms, freed from their hydrogen companions, begin to crystallize. You're witnessing the formation of diamonds. Not just tiny specks, but potentially massive crystals that form in the crushing depths and then fall like glittering hail through the supercritical hydrogen ocean. Imagine being surrounded by diamond snow, each crystal reflecting the faint light filtering down from above as it tumbles through the dense fluid around you. But here's the thing that really blows my mind about this process. These diamonds aren't staying small. As they fall deeper into Neptune's interior, they encounter more free carbon atoms and continue to grow. Some scientists think there could be diamonds the size of buildings slowly sinking through Neptune's interior, taking thousands of years to complete their journey to the core. Think about that for a moment. You're falling through a world where it literally rains diamonds, where the pressure is so intense that carbon atoms have no choice but to lock themselves into the hardest crystal structure known to nature. And you're just getting started on your journey to the bottom. At 500 kilometers down, the supercritical ocean around you has become incredibly dense. The pressure has reached levels that are hard to even comprehend. We're talking about thousands of times the pressure at the bottom of Earth's deepest ocean trenches. If you could somehow measure the density of the fluid around you, you'd find it's approaching that of liquid water, even though it's still made primarily of hydrogen and helium. The temperature, which has been holding steady at those frigid -200 degrees, finally starts to climb. But it's not climbing because of sunlight. You're now so deep that no solar radiation reaches you. The heat is coming from within Neptune itself, from the incredible pressure you're experiencing, and from the planet's mysterious internal heat source. Here's something that still puzzles scientists. At this depth, you should be in complete darkness. The faint sunlight that reaches Neptune, already less than 1% of what Earth receives, should be completely absorbed by now. But somehow, there's still a faint glow around you. It's not much, just enough to make out the swirling patterns in the supercritical fluid. But it's there. This glow might be coming from chemical reactions in the fluid around you, or from the heat being generated by the incredible pressure. Some scientists even think it could be coming from electrical activity, psi. Remember, you're moving through a conducting fluid in the presence of Neptune's bizarre magnetic field. You might literally be falling through a planet-sized electrical generator. At 800 kilometers down, your impossible journey takes another dramatic turn. The fluid around you is now so dense and under such pressure that it's starting to behave like hot metal. The hydrogen is being compressed into a state that doesn't exist anywhere on Earth, AB fluid, metallic hydrogen. It flows like mercury, but conducts electricity like copper. This metallic hydrogen ocean is probably where Neptune's magnetic field is generated. Unlike Earth, where our magnetic field comes from currents in our iron core, Neptune's magnetism appears to be created here, in this supercritical metallic ocean. The currents flowing around you are part of a dynamo system that creates magnetic field lines stretching millions of kilometers into space. You're now experiencing pressures of hundreds of thousands of times Earth's atmospheric pressure. The temperature has climbed to several hundred degrees above absolute zero, still incredibly cold by human standards, but positively tropical compared to where you started. And you're moving through a substance that's simultaneously liquid, metallic, and magnetic. But even at this depth, you're not even close to reaching Neptune's center. You've fallen more than 800 kilometers, experienced pressures and temperatures that would destroy any material created on Earth, witnessed diamond formation and metallic hydrogen, and you've barely scratched the surface of this world's mysteries. As you continue your descent, the metallic hydrogen ocean becomes increasingly exotic. The pressure continues to build exponentially, and new phases of matter that exist nowhere else in the solar system begin to appear around you. Water, ammonia, and methane, iomons, the few complex molecules that have survived the journey this far, start to behave in ways that would rewrite chemistry textbooks. At around 1,000 kilometers down, you encounter something that sounds like pure science fiction. Superionic ice. This is water that's been squeezed and heated to such extremes that the oxygen atoms lock into a solid crystal lattice, while the hydrogen atoms flow freely through it like a liquid. It's simultaneously solid and liquid, conducting electricity while maintaining a rigid structure. This superionic ice probably covers vast regions of Neptune's interior, creating layers of matter that can't be created in any laboratory on Earth. You're falling through a substance that challenges our basic understanding of what the different states of matter even mean. And the diamonds? They're still falling with you, some of them now massive crystals that have been growing for millions of years. They sink through the metallic hydrogen like stones through honey, following the same path you're taking toward Neptune's core, but moving much more slowly. A diamond that forms near the top of Neptune's atmosphere might take 10,000 years to complete the journey you're making in hours. As you pass the 1,500-kilometer mark, about halfway to Neptune's center, the environment around you has become completely alien. The pressure has reached millions of times Earth's atmospheric pressure. The temperature has climbed to over 1,000 degrees Celsius. You're surrounded by materials that exist nowhere else in the solar system, falling through an ocean of metallic hydrogen toward a core that's hotter than the surface of the Sunday. But perhaps the most amazing thing about your journey so far isn't the exotic matter or the extreme conditions. It's the realization that all of this, the diamond rain, the metallic hydrogen oceans, the superionic ice, exists in a world that we discovered through mathematics. Leverrier's calculations didn't just find a new planet. They found a completely alien realm where the normal rules of chemistry and physics are stretched to their absolute limits. And you're only halfway there. The second half of your journey, toward Neptune's core, will take you through conditions so extreme that matter itself begins to behave in ways that challenge our understanding of reality. You'll witness pressures that crush atoms into new configurations, temperatures that create exotic forms of ice that are harder than steel, and magnetic fields that are generated by mechanisms unlike anything on Earth. Your descent into the blue abyss has revealed that Neptune isn't just another planet. It's a laboratory for extreme physics, a place where nature conducts experiments that we can barely imagine, let alone reproduce. Every kilometer of your fall has taken you further from the familiar and deeper into the extraordinary. But we're just getting started. The most incredible discoveries are waiting in the depths below, where the true heart of Neptune beats with heat that shouldn't exist and magnetism that defies our understanding. The blue abyss has more secrets to reveal, and they're going to fundamentally change how we think about what's possible in our universe. August 25th, 1989, 3:29 a.m. Pacific Time. After 12 years of traveling through the void of space, Voyager 2 is about to make history. In a control room at NASA's Jet Propulsion Laboratory in Pasadena, a small group of exhausted engineers and scientists are about to witness something that will rewrite astronomy textbooks and shatter every assumption we had about the outer reaches of our solar system. Picture this scene for a moment. These aren't just any scientists. These are the people who have spent the better part of their careers planning this single encounter. Some of them have been working on the Voyager mission since the early 1970s. They've watched their spacecraft travel farther from Earth than any human-made object in history, threading the needle between Jupiter's radiation belts, surfing Saturn's gravity well, and then making the long, lonely journey to Uranus and finally to Neptune. And now, after 12 years of anticipation, Voyager 2 is screaming past Neptune at over 60,000 kilometers per hour, just 4,800 kilometers above the planet's cloud tops. That might sound like a lot, but in cosmic terms, it's like skimming the surface. One tiny navigation error, one small miscalculation, and the spacecraft would have crashed into Neptune's atmosphere and been crushed like a tin can. But here's what makes this moment even more remarkable. Every piece of data, every photograph, every measurement that Voyager 2 is taking right now won't reach Earth for another 4 hours and 6 minutes. That's how long it takes for radio signals to travel from Neptune to Earth, even moving at the speed of light. The scientists in that control room are watching events that happened 4 hours ago, like watching a live broadcast with the most extreme delay imaginable. So, when Ed Stone, Voyager's project scientist, sees the first clear image of Neptune appear on the monitors at 7:35 a.m., he's actually looking at a picture that was taken at 3:29 a.m. It's like having a conversation with someone on the phone who's 4 hours in the past. Everything you're seeing is history by the time it reaches you. And what they saw in those first images changed everything we thought we knew about Neptune. Before Voyager 2's encounter, most astronomers expected Neptune to be, well, boring. It was so far from the Sun, 30 times farther than Earth, that it received less than 0.1% of the sunlight that Earth gets. Basic physics suggested it should be a cold, dead world with maybe some faint cloud bands and not much else happening. Boy, were they wrong. The first thing that jumped out from Voyager's images was the color. Neptune wasn't just blue, it was brilliantly, vibrantly blue, more intensely colored than any planet they'd ever seen. The methane in its atmosphere was absorbing red light and reflecting blue with an efficiency that made the planet look like a perfect azure marble hanging in space. But then the details started coming in, and that's when jaws started dropping in mission control. Instead of the calm, cold atmosphere they expected, Neptune was raging. The planet was covered with massive storm systems, swirling cloud formations, and weather patterns that seemed to defy every model of atmospheric physics. Remember, this is a world that receives almost no energy from the Sunday. By all rights, there shouldn't be enough heat to drive any significant weather activity. And then they saw it. The Great Dark Spot. Picture an oval-shaped storm about the size of Earth, with winds racing around its edges at over 2,000 kilometers per hour. That's faster than the speed of sound. For comparison, the strongest hurricane winds ever recorded on Earth topped out at around 400 kilometers per hour. Neptune's Great Dark Spot was hosting winds 5 times more powerful than Earth's most extreme weather. But here's what really blew everyone's minds. Those winds weren't just fast, they were supersonic. The mathematical models said this was impossible. How do you get supersonic winds on a planet that receives virtually no energy from its star? Where was all this energy coming from? The answer, as it turned out, was coming from Neptune itself. As Voyager's instruments continued to take measurements, they discovered that Neptune radiates 2.6 times more energy than it receives from the Sunday. This distant, supposedly cold world was generating its own heat, enough to drive weather systems that made Earth's most powerful storms look like gentle breezes. Think about how significant this discovery was. We'd just found a planet that was essentially its own little heater, warming itself from the inside and creating weather patterns more extreme than anything in the solar system. It was like discovering that your refrigerator was actually a furnace. But the surprises were just getting started. As Voyager 2 swung around Neptune for its closest approach, the spacecraft's cameras turned toward Neptune's largest moon, Triton. What they found there sent gasps echoing through the control room. Triton was supposed to be a dead, frozen ice ball. It's smaller than our moon, orbits in the wrong direction, and receives so little sunlight that its surface temperature is minus 235 degrees Celsius. That's only 38 degrees above absolute zero, the coldest temperature possible in the universe. Nothing should be happening on a world that cold. But Voyager's cameras revealed geysers. Actual geysers, shooting columns of dark material 8 kilometers high into Triton's incredibly thin atmosphere. These weren't water geysers like the ones at Yellowstone. These were nitrogen geysers, powered by liquid nitrogen under Triton's surface that was somehow finding enough energy to explosively vaporize and burst through the ice. Let me put this in perspective for you. Imagine finding active volcanoes on Pluto. That's essentially what Voyager had discovered, geological activity on one of the coldest objects in the solar system. The textbook said this was impossible. Worlds that cold and small shouldn't have enough internal heat to drive any kind of geological processes. And yet there it was, captured in stunning detail by Voyager's cameras. Dark plumes of nitrogen and organic compounds shooting up from Triton's surface, creating thin, wispy clouds in its tenuous atmosphere before the material settled back down as dark streaks across the ice. The mission team was frantically trying to understand what they were seeing. Here was a moon that was rewriting the rules of planetary science in real time. Not only was it geologically active, but it had an atmosphere, thin, but definitely there. Nitrogen gas was sublimating directly from the ice surface into space, creating a barely detectable but measurable envelope around this distant world. But perhaps the most shocking discovery about Triton was its surface composition. Voyager's spectrometers revealed that Triton's south polar region was covered in frozen nitrogen, with traces of methane and carbon monoxide. The surface looked like nothing anyone had ever seen before. Vast plains of nitrogen ice marked by ridges, valleys, and what appeared to be frozen lakes. The terrain was so unusual that scientists had to invent new terms to describe it. They called it cantaloupe terrain because the surface was broken into polygonal cells that looked remarkably like the skin of a cantaloupe. But instead of being made of organic matter like a melon, this was nitrogen ice that had been cracked and reformed by geological processes operating at temperatures that would freeze air solid. Meanwhile, back at Neptune itself, Voyager was making discoveries that were equally mind-blowing. The spacecraft detected a magnetic field, which wasn't entirely surprising. Most large planets have magnetic fields. But Neptune's magnetic field was completely bizarre. Instead of being aligned with the planet's rotation axis like Earth's magnetic field, Neptune's magnetic field was tilted 47 degrees and offset from the planet's center by more than half its radius. It was as if someone had taken a normal planetary magnetic field and thrown it completely out of whack. This discovery forced scientists to completely rethink how planetary magnetic fields are generated. Earth's magnetic field comes from currents in our molten iron core, and it's nicely aligned with our rotation axis. But Neptune's offset, tilted magnetic field suggested something much more complex was going on. Multiple sources of magnetism, creating a field that didn't follow any of the standard models. As Voyager continued its flyby, the spacecraft also discovered that Neptune has rings, faint, dark rings that are barely visible but definitely there. But these weren't like Saturn's spectacular ring system. Neptune's rings were incomplete, forming arc-like segments rather than complete circles. It was another puzzle that didn't fit existing theories about how ring systems form and evolve. The ring discovery led to another surprise. Neptune has more moons than anyone expected. In addition to Triton, which had been known since 1846, Voyager discovered 6 new moons. These weren't large moons like Triton, but small, irregular objects that were probably captured asteroids or fragments from some ancient collision. But here's what I find most remarkable about Voyager's Neptune encounter. It all happened in just 6 hours. 6 hours of close approach, during which humanity's understanding of the outer solar system was completely revolutionized. 12 years of travel time for 6 hours of discovery that would keep scientists busy for decades. Think about the precision required to make this happen. Voyager 2 had to travel over 4 billion miles with such accuracy that it arrived at exactly the right place, at exactly the right time to make these discoveries. The spacecraft had to be navigated with pinpoint precision across distances so vast that a tiny error early in the mission would have meant missing Neptune entirely. And remember, this was 1989. The computers controlling Voyager 2 had less processing power than a modern calculator. The entire spacecraft was controlled by a computer with about 68 kilobytes of memory, no less than a single email attachment today. Yet this primitive by modern standards technology managed to deliver one of the most successful planetary encounters in the history of space exploration. As Voyager 2 raced away from Neptune, continuing on its trajectory toward interstellar space, the scientists back on Earth were left to process an enormous amount of data that would take years to fully analyze. But even in those first few hours, it was clear that everything they thought they knew about the outer solar system was wrong. Neptune wasn't a cold, dead world. It was a dynamic, active planet with extreme weather, mysterious internal heat sources, and a magnetic field that defied explanation. Its largest moon wasn't a boring ice ball. It was a geologically active world with an atmosphere and the most exotic terrain in the solar system. The discovery changed how we think about the entire outer solar system. If Neptune could be this active and dynamic at 30 times Earth's distance from the Sun, what did that mean for other distant worlds? What did it mean for our understanding of how planets form and evolve? These questions became even more important as astronomers began discovering planets around other stars. Many of these exoplanets are Neptune-sized worlds orbiting at various distances from their stars. Voyager's discoveries at Neptune provided crucial insights into how these alien worlds might behave and what conditions might exist in their atmospheres. But perhaps most importantly, Voyager's encounter with Neptune demonstrated the power of exploration itself. Before the flyby, Neptune was just a tiny blue dot in telescopes, a mathematical curiosity discovered through orbital mechanics. After Voyager, it became a real world with weather, moons, rings, and mysteries that are still being unraveled today. The mission proved that you can't understand a planet by looking at it from billions of miles away. You have to go there. You have to get close enough to see the details, to measure the magnetic fields, to watch the storms evolve, to discover the unexpected. Voyager 2's encounter with Neptune was a masterclass in the importance of actually visiting the places we want to understand. And here's something that gives me chills every time I think about it. Voyager 2 is still out there, still sending back data as it travels through interstellar space. The same spacecraft that revolutionized our understanding of Neptune is now exploring the space between the stars, sending back information about what exists in the void between solar systems. That 6-hour encounter at Neptune was just one chapter in an epic journey that's still continuing today, more than 30 years later. Voyager 2 has traveled farther from home than any human creation, and it's still teaching us about the universe we live in. But the legacy of that encounter with Neptune goes beyond just the scientific discoveries. It reminded us that our solar system is far stranger and more wonderful than we could have imagined. It showed us that even in the coldest, most distant reaches of our cosmic neighborhood, extraordinary things are happening. And it proved that sometimes the best way to understand the universe is to build something amazing and send it out to see what's really there. The data from Voyager's Neptune encounter is still being analyzed today, still yielding new insights into how gas giant planets work and what drives their remarkable weather systems. But more than that, it set the stage for everything we've learned about the outer solar system since. Every mission to the outer planets, every discovery about exoplanets, every model of planetary formation builds on the foundation that Voyager laid during those 6 incredible hours at Neptune. Next time, we're going to dive deeper into one of Voyager's most shocking discoveries, InDB, that backwards moon called Triton, and the violent story written in its orbit that tells us about cosmic catastrophes and the early history of our solar system. There's something deeply unsettling about a moon that orbits backward. In our solar system, where almost everything follows predictable patterns, when diace, planets orbit the Sun in the same direction, most moons orbit their planets in the same direction. The planets spin. Triton stands out like a cosmic rebel. It's the only large moon in the entire solar system that orbits in the wrong direction, and that backward dance tells one of the most violent and fascinating stories in our cosmic neighborhood. When I say Triton orbits backward, I mean it's moving in what astronomers call a retrograde orbit. While Neptune spins on its axis in one direction, Triton circles around it in the opposite direction. It's like having a car driving backward on a highway where all the other traffic is moving forward. In the orderly clockwork of planetary motion, this is profoundly weird. But here's what makes Triton's story even more compelling. It's not just any moon. This is a world larger than Pluto, with a diameter of 2,700 kilometers. We're talking about the seventh largest moon in the entire solar system, and it's moving in completely the wrong direction. That's not the kind of thing that happens by accident. The only way to get a large moon orbiting backward is through capture. Triton wasn't born in orbit around Neptune, TSF. It was stolen. Picture this. Billions of years ago, Triton was minding its own business, wandering through the outer solar system as a free-floating dwarf planet. It was probably very similar to Pluto, a ball of rock and ice with its own orbit around the Sun, following its own path through the cosmic wilderness. Then it made the mistake of wandering too close to Neptune. What happened next was gravitational theft on a planetary scale. Neptune's immense gravity reached out and grabbed Triton, yanking it out of its independent orbit around the Sun and forcing it into orbit around Neptune itself. But this wasn't a gentle process. When gravity captures an object as large as Triton, the results are catastrophic. Think about the physics involved here. Triton was moving at tremendous speed relative to Neptune, probably several kilometers per second. For Neptune's gravity to capture something moving that fast, it had to apply enormous forces over an extended period. The process would have been violent, chaotic, and devastating. And here's the most dramatic part of the story. Triton's capture destroyed Neptune's original moon system. Before Triton arrived on the scene, Neptune probably had a collection of regular moons, formed from the same disk of material that created Neptune itself. These moons would have orbited in neat circular paths in the same direction Neptune rotates, just like the major moons of Jupiter and Saturn. But when Triton came crashing into this orderly system, its massive gravitational influence wreaked havoc. The original moons were either ejected from the Neptune system entirely or smashed into fragments. The debris from these shattered worlds still orbits Neptune today as its ring system, faint, dark rings that are the graveyards of worlds that existed billions of years ago. This means that every time you look at Neptune's rings, you're seeing the remains of a cosmic catastrophe. Those particles of dust and rock circling Neptune are all that's left of moons that once orbited peacefully until Triton's arrival turned their world upside down. But Triton's story doesn't end with its violent capture. The process of being caught by Neptune's gravity also transformed Triton itself in dramatic ways. When Triton was first captured, its orbit was highly elliptical, DFS, stretched out into a long, oval shape that brought it very close to Neptune at some points, and carried it far away at others. This elliptical orbit subjected Triton to incredible tidal forces. Just like Earth's moon creates tides in our oceans, Neptune's much stronger gravity created tides in Triton's solid body. But these weren't gentle water tides. These were tides that flexed and squeezed Triton's entire rocky interior like a stress ball. The energy from this tidal flexing had to go somewhere, and it went into heat. Triton's interior was literally cooked by tidal forces, melting ice that had been frozen solid for billions of years. This heating process may have completely resurfaced Triton, erasing any evidence of its pre-capture history and creating the strange, smooth terrain that Voyager 2 observed. Over hundreds of millions of years, this tidal heating gradually circularized Triton's orbit, turning the elongated ellipse into the nearly circular path we see today. But the process extracted energy from Triton's orbital motion, causing the moon to gradually spiral inward toward Neptune. Triton is still spiraling inward today, getting about 3 centimeters closer to Neptune every year. Now, 3 centimeters per year might not sound like much, but when you multiply that by millions of years, the numbers become significant. And here's where Triton's story takes a dramatic turn toward the future. In about 600 million years, Triton will spiral close enough to Neptune that the planet's gravity will tear it apart. Picture this future catastrophe. As Triton gets closer and closer to Neptune, the tidal forces that once heated its interior will become strong enough to overcome the gravitational forces holding the Moon together. Triton will be stretched and pulled until it literally falls apart, breaking into countless fragments that will spread out around Neptune to form spectacular rings. These rings will be unlike anything we see in the solar system today. While Saturn's rings are made mostly of water ice and are relatively bright, Triton's rings will be made of rock and organic compounds, creating dark, dramatic bands around Neptune that could persist for millions of years before eventually falling into the planet's atmosphere. So, in the far future, Neptune will trade its largest moon for the most spectacular ring system in the solar system. It's a cosmic exchange that demonstrates how dynamic and ever-changing our supposedly stable solar system really is. But let's get back to the present, because Triton today is remarkable enough on its own. When Voyager 2 flew past this backward moon in 1989, it revealed a world unlike anything scientists had ever seen. The surface was covered in what they called cantaloupe terrain, bizarre polygonal cells that looked like the skin of a melon, but made of nitrogen ice instead of organic matter. This terrain tells us something incredible about Triton's composition. The surface is dominated by nitrogen ice, with traces of methane and carbon monoxide, IL, the same materials found on Pluto's surface. This similarity isn't a coincidence. Both Triton and Pluto are likely survivors from the same population of objects that formed in the outer solar system billions of years ago. The fact that Triton and Pluto are so similar provided scientists with their first real clue about what Pluto might be like, decades before the New Horizons mission actually visited the dwarf planet. When New Horizons flew past Pluto in 2015, many of its discoveries, AS, the nitrogen plains, the complex geology, the thin atmosphere, were predicted based on what we'd learned about Triton. But Triton had some surprises that even Pluto couldn't match. Those nitrogen geysers that Voyager discovered are still one of the most remarkable features in the solar system. Picture geysers shooting liquid nitrogen 8 kilometers high from a surface that's colder than anywhere on Earth. The energy driving these geysers comes from a combination of seasonal heating as Triton's southern hemisphere experiences its brief summer and from greenhouse warming beneath the surface. Here's how the greenhouse effect works on Triton. Sunlight penetrates a few meters into the clear nitrogen ice, where it gets absorbed and trapped. The ice acts like a natural greenhouse, concentrating the tiny amount of solar energy that reaches this distant world. When enough pressure builds up, the liquid nitrogen explosively vaporizes and bursts through cracks in the surface ice. These geysers carry dark organic compounds high into Triton's thin atmosphere, where the particles get caught by high-altitude winds and transported hundreds of kilometers before settling back to the surface. This creates the dark streaks that crisscross Triton's southern hemisphere, essentially pollution from nitrogen volcanoes. The atmosphere itself is another marvel. Despite being incredibly thin, about 1/70,000th the density of Earth's atmosphere, it's definitely there. Nitrogen gas sublimates directly from the ice surface, creating a tenuous envelope that extends several hundred kilometers above Triton's surface. This atmosphere even has weather, with seasonal changes as different parts of Triton receive varying amounts of sunlight during its long orbital period. What's particularly fascinating is that Triton's atmosphere is probably thicker now than it was when Voyager visited in 1989. As Triton approaches its southern summer solstice, more nitrogen ice sublimates into gas, gradually thickening the atmosphere. This process will continue for several more years before reversing as Triton's seasons change. But perhaps the most mind-blowing aspect of Triton is what its existence tells us about the early solar system. The fact that a Pluto-sized object could be captured by Neptune means that the outer solar system was once a much more chaotic and crowded place than it is today. During the early period of planetary formation, there were probably dozens or even hundreds of Pluto-sized objects wandering through the outer solar system. These objects, which scientists call planetesimals, were the building blocks of the giant planets. Most of them were either incorporated into the growing planets or ejected from the solar system entirely. But a few survivors, like Pluto and the other dwarf planets in the Kuiper belt, managed to find stable orbits where they could persist for billions of years. Triton was probably one of these survivors until its unlucky encounter with Neptune. The violence of Triton's capture also tells us something important about planetary migration. Computer simulations suggest that the giant planets didn't form in their current positions. Instead, they migrated inward and outward over millions of years, stirring up the early solar system and scattering small objects in all directions. During this period of planetary migration, encounters like the one that captured Triton would have been relatively common. The outer solar system was a shooting gallery of giant planets and large planetesimals, with gravitational interactions sending objects flying in all directions. Some of these scattered objects were ejected from the solar system entirely and now wander through interstellar space as free-floating planets. Others were sent into the inner solar system, where they may have delivered water and organic compounds to the early Earth, and a few, like Triton, found new homes as moons of the giant planets. This perspective makes Triton not just a fascinating moon, but a window into the violent history of our solar system. Its backward orbit is like a fossil record of ancient chaos, preserving evidence of events that happened billions of years ago. Every time astronomers observe Triton, they're seeing a survivor from the solar system's wild youth, when planets were still migrating and large objects were being scattered like cosmic billiard balls. The fact that Triton ended up as Neptune's moon, instead of being ejected into interstellar space or destroyed in a collision, is almost miraculous. And here's something that gives me chills. Triton's story might be playing out around other stars right now. As we discover more and more exoplanet systems, we're finding that planetary migration and gravitational chaos are common processes. Some of those distant worlds might have captured their own Tritons, backwards moons that tell stories of ancient violence and cosmic catastrophe. The study of Triton has also revolutionized our understanding of captured objects throughout the solar system. Many of the small, irregular moons of the giant planets are probably captured asteroids or comets, but Triton shows us what happens when the captured object is large enough to maintain its own geology and atmosphere. Looking at Triton today, with its nitrogen geysers and exotic ice geology, it's hard to imagine the violent process that brought it to Neptune. But that backward orbit never lets us forget that this remarkable world is a refugee from the outer solar system, a wanderer that found a new home through one of the most dramatic capture events in planetary history. In our next chapter, we're going to journey to the heart of Neptune itself, to explore the mystery of a planet that radiates more heat than it receives from the Sunday. We'll discover how a world so far from any heat source manages to generate enough energy to drive the most extreme weather in the solar system, and we'll explore the exotic states of matter that exist in Neptune's crushing interior. Here's a puzzle that's been driving scientists crazy for decades. Neptune radiates 2.6 times more energy than it receives from the Sunday. Think about what that means for a moment. This is a world sitting 4 billion miles away from our nearest star, receiving less than 0.1% of the sunlight that Earth gets. By all rights, it should be a frozen, dead ice ball drifting through the cosmic darkness. Instead, Neptune is generating its own heat. It's like discovering that your refrigerator has been secretly operating as a furnace, pumping out more energy than it consumes. In the physics of planetary science, this shouldn't be possible, and yet there it is, this brilliant blue world blazing with internal fire in the cold depths of space. To understand just how remarkable this is, let me put it in perspective. Earth receives about 1,300 watts of energy per square meter from the Sunday. That's enough to power a microwave oven. Neptune, on the other hand, receives about 1.5 watts per square meter, barely enough to power a small LED light bulb. At that distance from the Sun, Neptune should be getting just enough energy to maintain a temperature of about -220 degrees Celsius. But Neptune's actual temperature is -200 degrees Celsius, 20 degrees warmer than it should be. That might not sound like much, but in the physics of planetary atmospheres, those 20 degrees make all the difference between a dead world and a planet with the most extreme weather in the solar system. Think about this. Neptune is actually warmer than Uranus. Even though Uranus is 1 billion miles closer to the Sunday, Uranus receives twice as much solar energy as Neptune, but it's colder. This makes Neptune one of the most thermodynamically bizarre objects in our solar system. So where is all this extra heat coming from? The answer lies deep in Neptune's interior, in a process that transforms this distant world into something like a planetary furnace. The most likely explanation is that Neptune is still releasing heat from its formation 4.5 billion years ago. When planets form from the collision and accretion of countless smaller objects, the process generates enormous amounts of energy. All those impacts, all those gravitational collisions, create heat that gets trapped in the planet's interior. 4. Smaller worlds like Earth and Mars, this primordial heat was lost to space long ago. But for massive planets like Neptune, with 17 times Earth's mass, that heat can remain trapped for billions of years. The planet acts like a giant thermal battery, slowly releasing stored energy accumulated during its violent birth. But there's probably more to the story than just leftover heat from formation. Deep inside Neptune, heavier materials are still sinking toward the center while lighter materials rise toward the surface. This process, called differentiation, converts gravitational potential energy into heat, energy. Essentially, Neptune is warming itself by reorganizing its interior. Picture this happening on a planetary scale. Droplets of liquid rock and metal, formed under incredible pressure, slowly sinking through thousands of kilometers of compressed hydrogen and helium. Each droplet converts its gravitational energy into heat as it falls, adding to Neptune's internal furnace. This process could continue for millions or even billions of years. There's also the possibility that radioactive decay is contributing to Neptune's heat budget. While Neptune is mostly hydrogen and helium, it also contains heavier elements that were incorporated during its formation. Some of these elements, like uranium and thorium, are naturally radioactive and release energy as they decay. The exact contribution of radioactive heating is hard to calculate because we don't know the precise composition of Neptune's interior, but even a small amount of radioactive material, spread throughout a planet-sized volume, could generate significant heat over geological timescales. Whatever the exact mechanism, and it's probably a combination of all these processes, the result is a planet that's essentially heating itself from the inside out. This internal heat source is what drives Neptune's incredible atmospheric dynamics and creates weather patterns that make Earth's hurricanes look like gentle breezes. But here's where things get really interesting. This internal heat doesn't just warm Neptune's atmosphere, it fundamentally changes the planet's structure and the exotic states of matter that exist in its interior. Neptune's interior can be divided into 3 main regions, each more alien than the last. At the top, you have the atmosphere that we can observe from space, layers of hydrogen, helium, and methane that create Neptune's stunning blue appearance. This is the only part of Neptune that we can see directly, but it represents less than 20% of the planet's total mass. Below the atmosphere lies Neptune's mantle, a region of water, methane, and ammonia, under such incredible pressure that these normally familiar substances behave like hot metal. The pressure in this region exceeds 5 million Earth atmospheres, 5 million. Imagine the weight of the entire atmosphere pressing down on every square inch, multiplied by 5 million. Under these conditions, water stops behaving like the liquid we know on Earth. Instead, it becomes what scientists call a superionic fluid, a state of matter where oxygen atoms lock into a solid crystal lattice while hydrogen atoms flow freely through the structure like a liquid. It's simultaneously solid and liquid, conducting electricity while maintaining a rigid framework. This superionic water probably covers vast regions of Neptune's interior, creating an ocean unlike anything that exists on Earth. The hydrogen ions flowing through the crystal lattice of oxygen atoms conduct electricity, turning Neptune's interior into a giant electrical generator. This is probably where Neptune's bizarre magnetic field originates. At the very center of Neptune lies its core, a region of compressed rock and ice that's roughly the size of Earth, but with temperatures reaching 5,400 degrees Celsius, as hot as the sun's surface. The pressure at Neptune's core exceeds 70,000 times Earth's. Atmospheric pressure, enough to crush diamond into dust. Under these extreme conditions, even the basic properties of matter change dramatically. Carbon atoms from decomposing methane molecules are compressed into diamond crystals that rain down through Neptune's interior like glittering hail. These diamonds can grow to enormous sizes as they fall, potentially reaching the size of buildings before finally reaching the core. But the most mind-bending aspect of Neptune's interior is how these extreme conditions create materials that simply cannot exist anywhere on Earth. The superionic ice in Neptune's mantle is harder than steel, but flows like honey. The metallic hydrogen in the deep atmosphere conducts electricity like copper, but flows like water. These substances exist only under the crushing pressures and intense heat of gas giant interiors. The heat flowing out from Neptune's core creates convection currents that span thousands of kilometers, carrying energy from the deep interior to the surface. These currents are what drive Neptune's extreme weather patterns and create the supersonic winds that circle the planet. But here's something that really blows my mind about Neptune's internal heat source. It's incredibly efficient. The planet generates enough energy to drive weather systems more extreme than anything on Earth, using nothing but the slow release of gravitational energy and the decay of radioactive elements. It's like having a car that runs on the energy released by dropping pebbles into a very deep well. This efficiency has important implications for our understanding of other planets, both in our solar system and around other stars. Many of the exoplanets discovered by the Kepler Space Telescope are Neptune-sized worlds orbiting far from their stars. Understanding how Neptune generates its internal heat helps us predict what conditions might exist on these distant worlds. Some of these exoneptunes might be even more extreme than our own. Neptune, with stronger internal heat sources, creating atmospheric conditions that are completely alien to our experience. Others might be cooler and calmer, their internal fires having burned out long ago. The study of Neptune's internal heat also provides insights into the formation and evolution of gas giant planets. The fact that Neptune is still releasing primordial heat after 4.5 billion years tells us something important about how long planetary formation processes can continue. When we look at newly formed star systems with the Hubble Space Telescope or the James Webb Space Telescope, we're seeing gas giant planets that are still in the process of forming and releasing enormous amounts of heat. Neptune gives us a window into what these young planets might become as they age and cool over billions of years. But perhaps most remarkably, Neptune's internal heat source makes it one of the most dynamic and active worlds in the outer solar system. While Uranus, with its weaker internal heat source, has relatively calm weather, Neptune rages with constant storms and supersonic winds. The difference in internal heat between these two similar planets creates completely different atmospheric behaviors. This discovery has changed how we think about habitability in the outer regions of solar systems. Traditionally, astronomers focused on planets in the habitable zone, the region around a star where liquid water can exist on a planet's surface. But Neptune shows us that internal heat sources can create warm environments even at tremendous distances from a star. While Neptune itself is far too extreme to support life as we know it, the principle is important for understanding moons like Europa and Enceladus, which are kept warm by tidal heating from their parent planets. These moons harbour subsurface oceans that might support life, powered not by their star, but by internal energy sources. Neptune's internal heat also raises fascinating questions about the planet's future evolution. Will the heat source eventually run out, turning Neptune into a cold, dead world like Uranus appears to be? Or will gravitational differentiation and radioactive decay continue to warm Neptune for billions of years to come? Current models suggest that Neptune will remain warm for a very long time, possibly for the entire remaining lifetime of the solar system. The planet is so massive that even small amounts of radioactive decay and gravitational settling can generate significant heat. This means Neptune might continue to rage with extreme weather for billions of years into the future. The mystery of Neptune's heat source also highlights how much we still don't know about planetary interiors. Despite decades of study, we still can't precisely account for all the energy that Neptune radiates. There might be additional heat sources that we haven't discovered yet, or the processes we do understand might be more complex than our current models suggest. This uncertainty is one of the reasons why scientists are so eager to send another mission to Neptune. A dedicated orbiter could study the planet's heat flow in much greater detail, potentially solving the mystery of where all that energy comes from and how it's transported through the planet's interior. The internal heat of Neptune reminds us that planets are not just cold rocks and gas balls drifting through space. They're dynamic, evolving systems with their own internal energy sources and complex thermal cycles. Neptune, despite being 4 billion miles from the Sun, is one of the most thermally active worlds in our solar system. Next time, we're going to explore the extreme physics laboratory that Neptune's interior represents, where pressures and temperatures create states of matter that push the boundaries of our understanding of chemistry and physics. We'll discover how Neptune's crushing depths transform ordinary materials into substances so exotic they barely qualify as matter as we know it. At the heart of Neptune, pressure reaches 70,000 times stronger than the deepest ocean trench on Earth. To put that in perspective, if you could somehow transport a single sugar cube to Neptune's core, it would weigh as much as a pickup truck. These aren't just big numbers we're talking about. They represent conditions so extreme that they transform the fundamental nature of matter itself. Under these crushing pressures, the familiar rules of chemistry stop applying. Materials that we think we understand, water, methane, even hydrogen, begin behaving in ways that sound like pure science fiction. Neptune's interior is essentially a natural laboratory for extreme physics, conducting experiments that we can barely imagine, let alone reproduce on Earth. Let me walk you through what happens to ordinary matter under these extraordinary conditions, because the story of how pressure transforms substances is one of the most mind-bending aspects of planetary science. Let's start with methane, the molecule that gives Neptune its beautiful blue color. In Earth's atmosphere, methane is a simple gas. 4 hydrogen atoms bonded to a single carbon atom in a neat pyramid-shaped molecule. It's stable, predictable, and well-behaved. But as methane molecules get dragged down into Neptune's crushing interior, they encounter pressures and temperatures that literally tear them apart. The chemical bonds that hold the hydrogen and carbon atoms together can't withstand the extreme conditions. The molecules shatter, leaving individual carbon and hydrogen atoms to fend for themselves in the hostile environment. Here's where things get remarkable. Those liberated carbon atoms, freed from their hydrogen companions and subjected to millions of times Earth's atmospheric pressure, have no choice but to reorganize themselves into the most stable structure possible under those conditions. And that structure is diamond. We're talking about diamond formation on a planetary scale, not tiny specks of diamond dust, but potentially massive crystals that form in Neptune's interior and then begin one of the most extraordinary journeys in the solar system. These diamonds, some potentially as large as buildings, slowly sink through the liquid metallic hydrogen that makes up Neptune's mantle, falling like glittering rain toward the planet's core. The journey of a single diamond through Neptune's interior could take thousands of years. Picture a crystal the size of a skyscraper, slowly tumbling through an ocean of metallic hydrogen, growing larger as it encounters more free carbon atoms along the way. By the time it reaches Neptune's core, a diamond that started as microscopic carbon atoms could have grown to truly massive proportions. This diamond rain isn't just a fascinating curiosity. It probably plays a crucial role in Neptune's thermal evolution. As these heavy crystals sink toward the core, they release gravitational potential energy that gets converted to heat. This process might be one of the sources of Neptune's mysterious internal heat, helping to power the extreme weather systems that rage in its atmosphere. But methane decomposition is just the beginning of the chemical transformations happening in Neptune's interior. Let's talk about what happens to water under these extreme conditions, because the behavior of H2O in Neptune's depths is even more bizarre. On Earth, water exists in three familiar phases: ice, liquid, and vapor. We're comfortable with these states because they occur at pressures and temperatures that our bodies can handle. But Neptune's interior creates conditions where water enters what scientists call superyonic phases, states of matter that don't exist anywhere on Earth. In superyonic ice, the oxygen atoms lock into a solid crystal lattice, while the hydrogen atoms flow freely through the structure like a liquid. It's simultaneously solid and liquid, behaving like a metal while maintaining the structural framework of ice. This substance is harder than steel but conducts electricity like copper. Think about how weird this is. You have a material that looks and acts like a solid metal, but it's chemically still water. The hydrogen ions flowing through the oxygen lattice create electrical currents that contribute to Neptune's bizarre magnetic field. Essentially, Neptune has oceans of metallic water conducting electricity through its interior. The superyonic ice in Neptune's mantle probably exists at pressures exceeding 5 million Earth atmospheres and temperatures of several thousand degrees Celsius. Under these conditions, the normal rules of chemistry become more like suggestions. Molecules that would normally repel each other are forced into intimate contact, creating compounds that can't exist under any other circumstances. But perhaps the most exotic transformation happens to hydrogen itself, the most abundant element in Neptune's atmosphere. Under the crushing pressures of Neptune's deep interior, hydrogen undergoes a phase transition that sounds like pure fantasy. It becomes metallic. Metallic hydrogen is one of the holy grails of material science. On Earth, we've only managed to create tiny amounts of it for brief moments in laboratory experiments using pressures that are barely achievable with our most advanced equipment. But in Neptune's interior, metallic hydrogen exists by the Earth mass quantities. This isn't just hydrogen that conducts electricity. This is hydrogen that has been compressed so tightly that its electrons become delocalized, flowing freely through a lattice of protons like electrons in a metal wire. It flows like mercury, but has the chemical composition of the most abundant element in the universe. The metallic hydrogen in Neptune's interior is probably where the planet's magnetic field is generated. Unlike Earth, where our magnetic field comes from currents in our iron core, Neptune's magnetism appears to originate in its hydrogen-rich mantle. The flowing metallic hydrogen creates electrical currents that generate magnetic fields, but not in the neat, organized way we see on Earth. This brings us to one of the most puzzling aspects of Neptune's extreme physics, its completely bizarre magnetic field. Earth's magnetic field is like a bar magnet, with field lines that emerge from one pole, loop around the planet, and enter at the other pole. It's aligned with our rotation axis and centered on our planet's core. Neptune's magnetic field is nothing like that. It's tilted 47 degrees from Neptune's rotation axis and offset from the planet's center by more than half its radius. It's as if someone took a normal planetary magnetic field and threw it completely out of alignment. The explanation for this weirdness lies in the exotic materials I've been describing. Instead of having a single dynamo generating the magnetic field in Neptune's core, the planet appears to have multiple sources of magnetism operating in its mantle. Currents of metallic hydrogen and superionic water create a complex, multi-layered magnetic field that doesn't follow any of the simple models we use for Earth-like planets. This offset, tilted magnetic field has practical consequences for anything trying to navigate near Neptune. The magnetic field lines twist and spiral in ways that would confuse any compass, creating a magnetic environment unlike anywhere else in the solar system. If you were somehow flying a spacecraft through Neptune's magnetosphere, your navigation systems would go completely haywire. The study of Neptune's magnetic field has forced physicists to develop entirely new theories about how planetary magnetism works. The discoveries have implications that go far beyond Neptune itself. If not, they help us understand the magnetic fields of other gas giant planets and even exoplanets orbiting distant stars. But the extreme physics of Neptune's interior doesn't just create exotic states of matter, it also generates pressures and temperatures that would be impossible to recreate in any laboratory on Earth. At Neptune's core, pressures reach 70,000 times Earth's atmospheric pressure, while temperatures soar to 5,400 degrees Celsius. To put those pressures in perspective, imagine taking the entire weight of Earth's atmosphere and concentrating it into a space the size of a sugar cube. That's the kind of pressure that exists at Neptune's center. Under these conditions, even the structure of atomic nuclei might be affected. These extreme conditions have turned Neptune into a natural laboratory for studying matter under pressures that we can only dream of achieving on Earth. The physics happening in Neptune's core might help us understand fundamental questions about the behavior of matter under extreme conditions, potentially providing insights into everything from the interiors of neutron stars to the conditions inside nuclear reactors. The temperatures at Neptune's core, hotter than the surface of the Sun, are generated purely by compression and the slow release of gravitational energy. This is heat created not by nuclear fusion or radioactive decay, but by the simple process of matter being squeezed into smaller and smaller volumes. It's a reminder that pressure itself can be a source of enormous energy. These extreme conditions also create materials that challenge our basic understanding of chemistry and physics. In Neptune's interior, there are probably compounds and phases of matter that don't fit into any of our existing theoretical frameworks. We're talking about materials that exist nowhere else in the solar system, created by pressures and temperatures that push matter to its absolute limits. The study of these extreme conditions has led to breakthroughs in our understanding of planetary formation and evolution. The fact that Neptune can maintain such extreme internal conditions for billions of years tells us something important about how energy is transported and stored in planetary interiors. This research has also revolutionized our understanding of exoplanets. Many of the planets discovered around other stars are similar in size to Neptune, and understanding how extreme physics works in our own Neptune helps us predict what conditions might exist on those distant worlds. Some exo-Neptunes might have even more extreme internal conditions than our own Neptune, with higher pressures, creating states of matter that are completely alien to our experience. Others might have cooler interiors where different types of exotic materials form under different pressure and temperature regimes. The diamond rain, metallic hydrogen, and superionic ice in Neptune's interior represent just the beginning of what's probably a vast catalogue of exotic materials created by extreme conditions. Each layer of Neptune's interior probably contains substances that would revolutionize material science if we could somehow study them in detail. But here's what I find most remarkable about Neptune's extreme physics laboratory. It's been operating continuously for 4.5 billion years. Every second of every day since Neptune formed, these incredible pressures and temperatures have been transforming matter in ways that push the boundaries of what we think is possible. The processes happening in Neptune's interior are so extreme that they forced scientists to rewrite fundamental theories about planetary science, materials physics, and magnetism. Every measurement we make of Neptune reveals new mysteries and challenges our understanding of how matter behaves under extreme conditions. And perhaps most importantly, Neptune's extreme physics reminds us that our universe is capable of creating conditions far more exotic than anything we can imagine or reproduce. The familiar matter that makes up our everyday experience represents just a tiny fraction of what's possible when pressure, temperature, and gravity reach truly extreme values. The exotic materials in Neptune's interior, the metallic hydrogen, the superionic ice, the diamond rain, EBD, exist at the very limits of what matter can do while still remaining recognizable as the elements we know. Beyond these conditions, matter itself might break down into forms that we can barely comprehend. Neptune's role as a natural physics laboratory continues to yield new discoveries and insights decades after Voyager's encounter. Every theoretical breakthrough in high-pressure physics, every new understanding of exotic states of matter, helps us better interpret the incredible conditions that exist in this distant world's interior. In our next chapter, we're going to explore how Neptune's extreme physics connects to the bigger picture of planetary science and our search for understanding worlds beyond our solar system. We'll discover how this distant ice giant has become our key to understanding alien planets and the incredible diversity of worlds that exist throughout the universe. Here's something that might surprise you. When astronomers discover planets orbiting distant stars, most of them look more like Neptune than any other world in our solar system. In fact, planets Neptune's size or smaller account for about 80% of all known exoplanets. This means that our lonely, distant Neptune isn't just an oddball at the edge of our solar system. It's actually the most common type of planet in the galaxy. Think about the implications of that for a moment. All those science fiction stories about Earth-like worlds orbiting distant suns. The reality is that the galaxy is dominated by Neptune-like planets, ADAs, worlds of crushing pressures, exotic chemistry, and extreme weather systems. If you picked a random planet from somewhere in the Milky Way, it would probably be more similar to Neptune than to Earth. This discovery has completely revolutionized how we think about planetary systems and what kinds of worlds might exist throughout the universe. Neptune has gone from being our solar system's forgotten outer planet to becoming the key for understanding the most common type of world in the galaxy. The realization came from the Kepler Space Telescope, which spent years staring at distant stars and watching for the tiny dimming that occurs when a planet passes in front of its host star. What Kepler found was shocking. The galaxy is absolutely packed with planets that are between the size of Earth and Neptune. These worlds, which astronomers call sub-Neptunes and mini-Neptunes, appear to be everywhere. But here's the problem. We've only visited Neptune once, during Voyager 2's brief flyby in 1989. Everything we know about Neptune comes from those few hours of close observation, plus decades of telescopic studies from Earth. For the most common type of planet in the galaxy, our knowledge is surprisingly limited. This is why Neptune has become such a high priority for future space missions. Understanding Neptune isn't just about satisfying our curiosity about our own solar system anymore. It's about developing the tools and knowledge we need to understand alien worlds orbiting distant stars. The connection between Neptune and exoplanets goes deeper than just size. Many of the physical processes that make Neptune so extreme, the internal heat generation, the exotic atmospheric chemistry, the complex magnetic fields, probably occur on exoplanets throughout the galaxy. By studying these processes in detail on Neptune, we're essentially developing a handbook for understanding alien worlds. Take Neptune's internal heat source, for example. Remember how Neptune radiates more energy than it receives from the Sun, This same process probably occurs on many exoplanets, especially those that are young or massive enough to retain significant internal heat. Some exo-Neptunes might be even more extreme than our Neptune, with stronger internal heat sources creating atmospheric conditions that are completely alien to our experience. The diamond rain that we talked about earlier, that's probably happening on exoplanets too. Any world with methane in its atmosphere and sufficient internal pressure will experience the same chemical processes that create diamond precipitation on Neptune. There might be thousands of worlds throughout the galaxy where it literally rains diamonds, but the most important connection between Neptune and exoplanets involves atmospheric physics. Neptune's extreme weather systems, ETZOs, those supersonic winds and massive storm systems, are driven by the planet's internal heat and rapid rotation. Many exoplanets have similar characteristics, which means they probably host weather systems that make Neptune's storms look calm by comparison. Some exo-Neptunes orbit much closer to their stars than our Neptune orbits the Sunday. These hot Neptunes receive intense stellar radiation that heats their atmospheres to thousands of degrees. The combination of internal heat and external stellar heating probably creates atmospheric dynamics that are beyond anything we see in our solar system. Other exo-Neptunes orbit in the cold outer regions of their star systems, similar to our Neptune. But some of these distant worlds might be orbiting red dwarf stars that are much cooler than our Sun, creating atmospheric conditions that could be completely different from what we see on Neptune. The study of Neptune's magnetic field has also become crucial for understanding exoplanets. The offset, tilted magnetic field that makes Neptune so unusual might actually be common among Neptune-sized planets. If most exo-Neptunes have similarly complex magnetic fields, this has important implications for their atmospheric evolution and potential habitability. Magnetic fields protect planetary atmospheres from being stripped away by stellar winds. A planet with a weak or misaligned magnetic field might lose the atmosphere over time, while a planet with a strong, stable magnetic field might retain its atmosphere for billions of years. Understanding how Neptune's magnetic field works helps us predict which exoplanets might maintain thick atmospheres and which might become barren worlds. The composition of Neptune's atmosphere also provides crucial insights for exoplanet studies. The methane that gives Neptune its blue color is one of the most important molecules for understanding planetary atmospheres. Methane is relatively easy to detect in exoplanet atmospheres using current telescopes, and its presence tells us important things about a planet's temperature, pressure, and chemical processes. But methane is also biologically significant. On Earth, most atmospheric methane is produced by living organisms. While the methane on Neptune is clearly not biological in origin, the study of how methane behaves in extreme planetary atmospheres helps us understand what to look for when searching for signs of life on exoplanets. Some exoplanets might have atmospheric conditions where methane can exist stably for long periods, while others might have conditions that quickly destroy methane molecules. By understanding these processes on Neptune, we're developing the tools to interpret methane detections in exoplanet atmospheres and determine whether they might indicate biological activity. The potential for life in Neptune-like atmospheres is actually more intriguing than you might think. While Neptune's extreme conditions make life as we know it impossible, some scientists have speculated about the possibility of aerial organisms that could float in the more temperate layers of Neptune's atmosphere. These hypothetical organisms would need to be very different from Earth life, probably more like floating chemical systems than anything we'd recognize as living. But the basic principles of chemistry and energy that would allow such life to exist might also apply to some exoplanets, with less extreme conditions. The study of Neptune's atmospheric chemistry has revealed complex hydrocarbon molecules that form when methane is broken down by radiation and pressure. These same processes probably occur on many exoplanets, potentially creating the building blocks of life in atmospheric environments that are completely alien to our Earth-based experience. Future missions to Neptune would revolutionize our understanding of exoplanets. A dedicated orbiter that could study Neptune for several years would provide detailed data on atmospheric dynamics, internal structure, magnetic field evolution, and chemical processes that occur in Neptune-like environments. The proposed Neptune Odyssey mission would do exactly that, orbit Neptune for several years while dropping probes into its atmosphere and studying Triton up close. The data from such a mission would provide a detailed template for understanding the thousands of Neptune-like worlds that we're discovering around other stars. But even before we send another spacecraft to Neptune, our understanding of this distant world continues to improve thanks to advances in telescopic technology. The James Webb Space Telescope, with its incredible sensitivity to infrared light, is already providing new insights into Neptune's atmospheric composition and dynamics. These observations help us refine our models of how Neptune-sized planets work, which in turn helps us better interpret the data we're collecting from exoplanets. It's a feedback loop where better understanding of Neptune leads to better understanding of alien worlds, which in turn helps us ask better questions about Neptune. The search for potentially habitable exoplanets has also highlighted the importance of understanding Neptune-sized worlds. While these planets are probably too massive and too gas-rich to support life on their surfaces, many of them might have moons that could be habitable. Just as Jupiter's moon Europa and Saturn's moon, Enceladus, might harbour subsurface oceans, the moons of exo-Neptunes might provide environments where life could evolve and thrive. Understanding how Neptune's tidal forces affect Triton helps us predict what kinds of conditions might exist on the moons of distant Neptune-like planets. The diversity of Neptune-like exoplanets also tells us something important about planetary formation processes. Our solar system has two ice giants, Neptune and Uranus, planet. But many exoplanet systems have multiple Neptune-sized worlds, sometimes orbiting much closer to their stars than our ice giants orbit the Sunday. This suggests that Neptune-like planets can form and migrate in ways that we're only beginning to understand. Some might form far from their stars and then migrate inward, while others might form close to their stars and remain there. Understanding these migration processes helps us piece together the history of planetary system formation throughout the galaxy. Perhaps most remarkably, Neptune has become our laboratory for understanding atmospheric escape, the process by which planets lose their atmospheres to space. Some exo-Neptunes are so close to their stars that they're literally evaporating, leaving behind rocky cores that might look more like super-Earths. By studying how Neptune's atmosphere interacts with the solar wind and cosmic radiation, we're learning about the processes that determine whether a planet can hold on to its atmosphere over cosmic timescales. This knowledge is crucial for understanding the long-term evolution of exoplanets and predicting which worlds might remain habitable for billions of years. The story of Neptune as a gateway to understanding alien worlds is really just beginning. As we discover more exoplanets with increasingly sophisticated telescopes, Neptune provides the foundation for interpreting what we find. Every new measurement of Neptune's atmospheric composition, every new insight into its internal structure, every new understanding of its magnetic field helps us better understand the thousands of Neptune-like worlds that populate our galaxy. In many ways, Neptune has become our cosmic Rosetta Stone, the world we can study in detail that helps us decode the mysteries of distant planets we can barely detect. The lonely ice giant at the edge of our solar system has transformed into one of our most important guides for understanding the universe beyond. This distant world, discovered through mathematics and visited only briefly by a single spacecraft, holds keys to understanding planetary systems throughout the galaxy. Neptune isn't just the eighth planet in our solar system, it's our window into the most common type of world in the universe, and our best hope for understanding what kinds of strange and wonderful planets might be waiting to be discovered among the stars. From mathematical prediction to cosmic laboratory, Neptune's journey in human understanding reflects our own journey from wondering about distant worlds to actually beginning to understand them. And that journey is far from over. The best discoveries about Neptune and the alien worlds it helps us understand are probably still waiting to be made.